Hello, welcome to our next lesson in Chapter 16. Up until this point, we've been doing a deep dive into line integrals. In this video, we're mostly going to take a break from line integrals. They'll pop up here and there, make a guest appearance, but for the most part, they're not going to be a large part of this lesson. This lesson really has two objectives. We're going to learn about curl and we're going to learn about divergence. What does curl mean? What does divergence mean? And how do we calculate them? So let's start with, let F be some vector field. Has a function to define the I component, J component, and R component. Then the curl of F is going to be the gradient operator crossed with F. The gradient operator crossed with F. And you'll see what I mean when we do this first example. What is curl? Well, curl relates to the rotational properties of a fluid at a point. Now, quick note, if we're taking two vectors and crossing them, that should show us that curl is going to give us a vector. So let's see this in action. Let's find the curl of F for that given vector field in example number 1. So what we're doing to find curl of F, we're going to take the gradient operator and we're going to cross it with F. And so hopefully you remember how to find a cross product from a few units ago. We're going to set up a matrix and we're going to find the determinant of that matrix. So we have I, J, K. Curl then is the partial with respect to X, the partial with respect to Y, and the partial with respect to Z. And then we can put our components, XZ, XYZ, negative Y squared. And we are finding the determinant. I'm going to do a quick review of how to find the determinant because I would venture to guess that some of us have forgotten. So what we're going to do is we're going to start by ignoring the first row, first column. So we have this little matrix here and we're going to find the determinant of it. We're going to do the diagonal, multiply, subtract the diagonal this way. And so we're going to take the partial with respect to y of negative y squared, and we're going to subtract the partial with respect to z of xyz. Then we're going to stay with that first row, ignoring the second column, again doing the diagonal. When you get to that second one though, remember it's going to flip the sign. So now we have the partial with respect to x of negative y squared, subtract the partial with respect to z of xz. And then for our third component, ignore the first row still, last column. So that's going to give us the partial with respect to x of xyz, subtract the partial with respect to y of xz. So now taking those partials, I'm going to get negative 2y, subtract xy, negative 0, subtract x, and yz, subtract 0. So finally, that gives us the curl of f. If I factor out a negative y, that first component then becomes 2 add x, second component is x, last component is yz. So, like we talked about earlier, remember, curl of f, you're going to get a vector field. Okay, so let's move on to a theorem that involves curl. The theorem is that the curl of the gradient of some function f is going to give us the 0 vector. So that's why that 0 is bolded, is it's going to give us the 0 vector. So we haven't done a proof in a little bit, so we're going to prove this. Now, note this note to the side. F, of course, must have continuous second-order partials. Okay, so let's jump into this proof. So we're going to start with curl of gradient of f. Curl is the gradient crossed with whatever we're taking the curl of. So then if we set this up, that x is a cross product, not the variable x. If we set this up, we're going to get ijk. So then our gradient operator is the partial with respect to x, the partial with respect to y, the partial with respect to z. And then the gradient of f is the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. Okay, so now if we're ready to compute this, doing the exact same thing that we did above. So we're ignoring the first row, first column, so we're going this direction, that direction. We get the second partial of f with respect to y and then respect to z, subtract the second partial of f with respect to z with respect to y. Second component, remember, we're switching the signs, so we're ignoring the first row and the second column. So we're going to get the second partial of f with respect to x and with respect to z, subtract the second partial of f with respect to z and with respect to x. And then lastly, second partial of f with respect to x with respect to y, subtract second partial of f with respect to y with respect to x. So the question is, can we simplify this? Well, if you remember, it says f must have continuous second order partials. And if you remember when we started to do partial derivatives, if we differentiate with respect to y and then z, exactly the same as z and then y. So these two quantities are the same. These two are the same. These two are also the same. So this gives us 0i, add 0j, add 0k, or just the 0 vector. Okay, so where this is logically going to lead us to is why do we actually care? So why do we care that the curl of the gradient of a function will give us the 0 vector? Well, that's right down here. If f is a conservative vector field, then remember, there exists some potential function that when we take the gradient, we're going to get the vector field of f. So what this theorem is also saying is that if f is conservative, then the curl of f, the curl of our vector field, is going to give us the 0 vector. So let's keep moving and use this fact then. So here's our next theorem. If f is a vector field defined on all of R3, so this just means in 3 space, so f is defined on all of 3 space, whose component functions have continuous partial derivatives, and curl of f is equal to the 0 vector, then f is a conservative vector field. So if we can show that the curl of a vector field is the 0 vector, then we know that that vector field is a conservative vector field. So let's look at the next example, which is going to show this theorem in action. Show that f, which is that given vector field, is conservative, and find the potential function. So what we would have done before we only had a vector field generally that was in 2 space, and it was written as p multiplied by I, add q multiplied by j. And so what we would have done is we would have taken the partial of p with respect to y, partial of q with respect to x, and we would have shown that they're equal. Now, what do we do if there is a vector in 3 space? We can't use this idea anymore. We could jump in and just try to find the potential function. But now what we're going to do instead, since we have 3 space, we can show that the curl of our vector field is the 0 vector. So that's what we're going to do. As a reminder, curl of f is just going to be the gradient operator crossed with f. I'm going to start by writing the functions just so that I make sure I have enough room. So then we get 2xy z cubed, 3xy squared z squared. So this is I, j, k. I have the partial with respect to x, the partial with respect to y, partial with respect to z. Okay, so then when I compute this, I'm not going to show all of the work, but I will show you the partial this way, the partial this way, and then we can simplify. So the first partial ends up being 6xy z squared, and then I'm subtracting 6xy z squared. Remember, the middle term is going to flip signs, so I get 3y squared z squared, subtract 3y squared z squared. And then we also have 2yz cubed, subtract 2yz cubed. So hopefully we can see that the curl of f in this case is the 0 vector, which tells us that f is a conservative vector field. Okay, so now that we know that f is a conservative vector field, we can find the potential function. You can start with any of these partials, it doesn't matter. For ease sake, I'm just going to start with the partial with respect to x, which is that y squared z cubed. So then I'm going to integrate with respect to x. So that gives me x y squared z cubed, and then I have some constant in terms of y and z. So now if you remember, what we're going to do is we're going to take the derivative with respect to either y or z. I'm going to do y, so this would give me 2xyz cubed, add k prime of yz. The partial with respect to y, we already know from the initial vector field that we were given. So this is 2xyz cubed, which tells us that our k prime of yz is just 0. So if we integrate, our k of yz then is just some function in terms of z. Well, obviously I ran out of room. Hopefully you used your room better than I did. I'm going to continue up here. So right now what we have for f, which comes from here and here, is we have that f is equal to x y squared z cubed, add k of z. So lastly, I'm going to take the derivative with respect to z, which is 3x y squared z squared, add k prime of z. We can see again that we get k prime of z to be 0, so hopefully you can end up seeing that this really just is going to end up being a constant. So where this finally leads us to is that our potential function is x y squared z cubed, and then there could be some constant. I have a few quick notes for you. In this example, both of these ended up being 0, and you would have ended up with a 0 here again, so we just ended up with a k. Nothing else got added on to our potential function as we were integrating. That's not always going to be the case. So this is not always the case. If you are in my class, I will tell you the problems that you get on WebAssign, that's always going to be the case, but not in the packet and not on your assessments. So not in your packet and not on your assessments. So don't expect this number to always be 0 so that you're always just getting a constant. And then the last thing is, if you're in my class, when you're doing WebAssign, you're not going to enter that into your potential functions. You're just taking k to be 0. So all you would enter is this part. Okay, so that's curl. Now we're going to move on to divergence. Divergence of f is the gradient operator dotted with the vector field. Okay, so a quick reminder, if we're dotting two vectors, we're going to end up with a scalar. You're not going to end up with a vector field. And divergence relates to the way in which a fluid flows away or towards a point. Okay, so we're going to look at the same vector field that we had in example number 1. And we're going to find the divergence of f. So from above, the divergence of f is going to be the gradient operator dotted with f. So gradient is partial with respect to x, partial with respect to y, partial with respect to z, dotted with xz, xyz, negative y squared. So the divergence here of f, partial with respect to x multiplied by xz is just z. Partial with respect to y ends up being xz. Partial with respect to z ends up being 0. So then divergence of f ends up being z add xz. This quantity right here is called a scalar field. So you're going to see that moving forward in your homework, but that's called a scalar field. Okay, so as you can see, divergence is pretty easy to calculate. We're not going to go too deep into it. At this point, we're going to talk about some more notation, and we're going to touch on Green's theorem a little bit, and then that'll be the end of these notes. So the next thing we want to talk about is what's called the Laplacian, which is just another operator. The Laplacian is like the gradient operator, but squared. And so what that's doing is it's taking the gradient operator and it's dotting it with the gradient operator. which gives us the second partial with respect to x, add the second partial with respect to y, add the second partial with respect to z. So if we applied it to f of x, y, z, so the Laplacian applied to some function, that would give us the second partial of f with respect to x, add the second partial of f with respect to y, add the second partial of f with respect to z. So the way then that we can write the Laplacian of f, that's really the divergence of the gradient of f. Okay, last thing we're going to touch on the next page, we're going to go back to Green's theorem for a little bit. Okay, so we're going to look at vector forms of Green's theorem. Consider that you have f, which is some vector field in 2 space. Suppose all the conditions for Green's theorem are satisfied. So remember, for Green's theorem, we have some curve that is closed, and it is simple, and it is oriented in a positive manner, so in a counterclockwise direction. That's what we're talking about. Then, so this little circle, remember, tells us that we can use Green's theorem, that we have a closed curve. It doesn't tell us the orientation, but closed curve. And then we have a line integral of f dot dr. If you remember, we could turn that into line integral of p dx at q dy, which what we really liked is we could turn it into a double integral of qx subtract py. So if we want to set up the curl of f, we're going to have ijk, partial with respect to x, partial with respect to y, partial with respect to z. And the first component is a function of x and y, the second component is a function of x and y, and the third component is 0, so that's off of our vector field above. So then if we notice, for the first component, we're going to get 0 subtract 0. For the second component, we're going to get 0 subtract 0. So all we end up with is the partial of q with respect to x, subtract the partial of p with respect to y, times the k component. So what that leads us to, right, this is what we see above. What that leads us to is that we can rewrite Green's theorem. So here again, we have line integral, we have a closed simple curve of f dot dr. We can write that as the double integral over the region D of curl of f, so that's this part like we talked about, times k dA. Now, the question is, why do we have to multiply by this k? Well, curl of f, if you remember, is going to give us a vector. That's not what we have up here. We don't want a vector. So if we multiply by k now, we take the dot product with k, this will be a scalar field. So then this becomes curl of f we talked about above, partial of q with respect to x, subtract the partial of p with respect to y, times k, and we're dotting with k dA, which again gives us double integral over the region D of the partial of q with respect to x, subtract the partial of p with respect to y dA. Okay, so that's just a fun fact for you, that we can write Green's theorem in terms of vectors. If you are not one of my students, you don't need to listen to this last part, but if you are one of my students, you're going to want to hear this. Some homework notes for you. The first problem is you're going to have some of these on the homework that say, let f be a scalar field and big F be a vector field, describe the following. And so what it means by something like this, if we take the divergence of a vector field, so we take the gradient vector and we dot it with the vector field, what we're going to get is, like we said, a scalar field. But then if we take the divergence of little f, so again, we're taking the gradient operator and we're dotting it with little f, well, little f is just a function. We can't take a vector and dot it with a function. So in that case, this is meaningless. So that's just an example. You have a question on the homework that's longer than that, but that's an example of what that question is looking for. And then you might need help with problem 3 on the homework. If you do, please ask. Well, thank you for sticking with me. Moving forward after this video, we are are going to be done with line integrals for the most part. They're going to make some guest appearances, but we'll be moving on to something called surface integrals. So I'll see you next time.